Okay, good morning, Professor David J. De Los Reyes. Okay, it's August 7 already. The time is 2 a.m. in the morning. Okay, my topic for this morning will be alternating current circuit, and this will now be lesson number 14. So we are running smooth on alternating current circuit. Okay, this topic for this morning will be an important for those who will be planning to be an electrical engineer, okay? Because in the calculation or the design calculations of current, okay, in the computation of the current, because the number one, what do you call this, function of an engineer is to compute for the total current consumption of any household or any business enterprise. Okay, let's proceed. So this is a long video format topic. This is alternating current circuit, lesson number 14. And the title of the topic is example problem on series impedance. Meaning, if the loads are still connected in series, okay, we are asked so many things. Like in this one here, we are asked so many things. 1, 2, 3, 4, 5, 6. It's a must for a design engineer to know these 6 things here. And the proper solution will be what we will do for this morning. Okay, let's proceed. We are given an example problem. I will try to read the problem, okay? Series connected loads, meaning to say we are given a series connected loads. The connection is series. Load number 1, load number 2, and load number 3. In the actual practice of electrical engineering, it might not only be 3 loads maybe. There are lots of loads, okay? But for this given example, I will just give you 3 loads that are connected in series. Okay, load number 1. Load number 1, it has a resistance of 25 ohms. L will be 39.78 millihenry. L is an inductance, a coil. Oh, so it could be a motor load maybe. Okay. Load number 2. What is given is the total value of the impedance. It's 15 ohms. The power factor is 80% and it is lagging. So from the description of the power factor, it is lagging. So supposed to be load number 2 is also a motor load. Okay, it's a motor load. This is a motor load and this is also a motor load. For load number 3, the resistance is 5 ohms and capital letter C is with the value 331.56 microfarad. This letter C here refers to the capacitance, okay? So load number 3 is actually a capacitor, or it could be a synchronous motor that is overexcited that acts like a capacitor. So for load number 3, okay, it could be a capacitor, pure capacitor maybe, and a synchronous motor that is overexcited. Okay, because we are given the value of the capacitance, right? So it could be a pure capacitor or it could be a synchronous motor, okay, that is overexcited to act like a capacitor. Okay, so the value for load number 3 is 5 ohms, capacitance is 331.56 micro. This is the symbol for micro, right? And this is actually 10 to the negative 6. Okay, so this one, it is a microfarad. Okay, the source voltage is 440 volts, angle 0 degree volts, and the frequency is 60 hertz. The problem is asking for the value of capital letter C with subscript T, meaning total impedance. Capital letter I with the subscript capital letter T, meaning the total current. So this should be the total current. Okay. Number 3 will be capital letter P with the subscript capital letter T, meaning total true power. Next one is capital letter Q with the subscript T, meaning total reactive power. Next one is capital letter S with the subscript capital letter T, meaning total apparent power. And the last one is PM, meaning power factor. The problem has got additional condition. Draw all vector diagrams. Okay, let's proceed with the solution. To bring out the solution, if you are on the board exams, okay, the solution will be something like this. I have taken my board exams already, and I presented the solution, and I passed the board exam. Okay, let's try to bring out the figure. An alternating current source, voltage is 440, frequency 60 Hz. Connected in series with the alternating current source is 3 impedances or 3 loads, which is designated by Z1, Z2, and Z3. So this could be load number 1, load number 2, or load number 3. And we are given the specifications of the 3 loads. Load number 1 is a motor load. Load number 2 is also a motor load. And load number 3 is a pure capacitance, or it could be a synchronous motor that is overexcited to act like a capacitor. So this is a motor load. This is also a motor load, and this is a capacitance, or it could be a synchronous motor. Right? Okay, let's try to bring out the solution. The solution, if you want to pass the board exams, your solution should be as neat as this one. So write as legibly as you can. Okay, bring out the solution. Load number 1. The given resistance of load number 1 is 25 ohms. Okay, we are given the inductance. So X of L will be 2 pi FL. So 2 pi times 60 times L. The unit of the inductance is actually millihenry. Milli is actually equal to 10 to the negative 3 Henry. This is millihenry, right? So this is 39.78 millihenry. So this is multiplied by 39.78 times 10 to the negative 3. So be sure to know your calculator, the usage of your scientific calculator. So these are all multiplications, right? 2 pi times 60 times 39.78 times 10 to the negative 3. Okay? If you try to multiply this in your calculator, this is exactly 15 ohms. Okay? So if we try to draw the vector diagram, because the problem says draw all vector diagrams. For load number 1, it is an inductive load. So the triangle will be this. The real part will be 25 ohms. It represents the resistance. The imaginary part is the inductive load, which is X of L, right? So it goes upward. So this is plus G15 ohms. The vector sum of 15 and 25 will give us Z1. Okay? That's the vector diagram. So this is trigonometry. So trigonometry got a function in the study of alternating current circuit. So what you know on the sine, cosine, tangent, you use in here. Okay, load number 2. For load number 2, the total impedance is 15 ohms. Okay, but we are given the power factor. Okay, from one of the definitions of power factor, it will be the ratio of R over Z. Okay, so if we try to compute for R, Because we are given, say, we are given the power factor. So we could actually compute for R. So R now will be Z times power factor, Z times power factor, 15 times 0.8, exactly this is 12 ohms. Okay? So how could we compute for the value of X of L? We computed the value of R to be 12 ohms. The impedance for load number 2 is 15 ohms. We are looking for this side here. So it seems we are given the hypotenuse in the adjacent side. So using Pythagorean theorem, the square of this should be equal to the sum of the square of this. And if we try to compute for this, X of L should be the square root. The square of this minus the square root 12, then take the square root. And X of L is exactly 9 ohms. So this is 9 ohms. Okay. Load number 3. For load number 3, the resistance is 5 ohms. But instead of giving us the impedance, what is given, the other given, or load number 3 is the capacitance, the other component of the load, in which the value of the capacitance is 331.56 microfarad. Micro is 10 to the negative 6. Right? So if we try to draw the the vector diagram of the impedance for load number 3, this is 5 ohms, right? And for this portion here, we could compute for this one. Because this part here is the J X of C, right? And X of C, one of the formula on how to compute for the reactance is X of C, that is 1 over 2 pi F C. Right? So we are given frequency and C, meaning the capacitance. So this is 1 over 2 pi times 60 times the value of the capacitance is 331.56 microfarad. Microfarad, this is micro, so this is 10 to the negative 6. So we will replace this micro here by the value 10 to the negative 6. Okay? If we try to simplify this one, then take the ratio, what will come out will be 8 ohms. Okay? So for the vector diagram of load number 3, we are now given this side, right? We are given the real part or the resistance. So C3, actually we don't need the absolute value of the impedance, but I just computed just for concept purposes, the square of pi plus the square of 8. So 25 plus 64, that will be 89. The square root will be 9.43. So the magnitude of the impedance for load number 3, we don't even need Z3. Because what we need is the real part and the imaginary part in the computation of the total impedance. So, number 1, if we try to compute for the total impedance, it will be the value of Z1, Z2, and Z3, but they should be all in rectangular form. And we have done that already. Z1 is 25 plus G15. 25 plus G15. Z2 will be 12. The value of R is actually 12. Where is 12? This 12 plus G9. 12 plus G9. And the value of C3 in rectangular form, it should be this 5 minus G8. This is 5 minus G8. The operation is addition, right? So using our knowledge of algebra, okay, try to combine similar terms. Real, real, real. So this is 25 plus 12 plus 5 plus quantity plus J. We combine the imaginary part. We bring out the common factor J. So this should be 15, 9, and minus 8. Simplifying this one, this is 42 plus G16. And the total value of the total current. The total current is not 42 and it is not 16. It should be the vector sum of 42 and 16. Okay? Because it is a, what they call this, right triangle, right? This is 42 and this is 16, and the total impedance should be the vector sum of this side here and this side. Okay? So like what I told you, you divide 16 by 42, we could compute for this angle here. And this is 20.85 degrees. Okay? So the first solution on how to compute for the magnitude will be take the cosine of this, divide that value to 42. What will come out will be 44.94. Or take the sine of this angle here. You divide that to 16. What will come out will still be 44.94. Or the third solution, take the square of 42, then take the square of 16. You add that one, then take the square root. What will come out should be 44.94. In the board exams, you do not have to bring out the solution of this one. Just perform the 3 solutions on your calculator, whatever solution you want to use, okay? I am just presenting the 3 solutions. Okay, so we are now given the total impedance. So total current will be the voltage of the source over total impedance. Because we have compressed this one already. We compressed it already, right? As a single impedance C total. And that C total is actually this one. 44.94, 20.85. So after compressing C1, C2, and C3, to take the total current, just take the applied voltage divided by the value of the total impedance. So the total current will be 440 angle 0 degree over 44.94 angle 20.85 degrees. Polar form, okay? 440 over 44.94 will be 9.79 and 0 minus 20.85 will be negative 20.85 degrees. And what is the significance of this current here? Meaning to say, the resulting total current lags the applied voltage by an angle 20.85 degrees. And if we try to bring out the vector diagram, this is the applied voltage. It is horizontal, right? And the angle lags this E here by an angle negative 20.85 degrees. It seems it is like this. If this is the applied voltage, okay, the current lags the applied voltage by 20.85 degrees, so it will oscillate like this. And this angle of difference here, this one, this portion, it is 20.85 degrees. You could see that on the oscilloscope, right? There is an angle of difference between the start of the two sine waves, okay, with an angle of 20.85 degrees. That's the meaning of this. Okay, the total true power, this is now an AC jam. Total true power will be the square of the current times R. The R we are referring here should be the R of the total impedance. This 42 here. Right? So this should be 9.79 squared times 42. This should be 4,026 watts. It is this portion here. And for Q total, because this is the resulting impedance, right? The total consumption of this one will be the square of the current times 16. So this should be 9.79 squared times 16. This is 1534 bars. Reactive volt ampere. Okay? So for this portion here, the unit is actually bars. Okay? Reactive volt ampere. Okay? And for S total, it's the same. The square of the total current times the value of the impedance, 9.79 squared times 44.94. Okay? What will come out will be, of course, S total will be greater than P total and Q total. This is 4307 volt ampere. This is this portion here. Volt ampere. The unit of apparent power is volt ampere, the product of voltage and current. Okay? And for the power factor, the definition of power factor, one definition, right? It is the ratio of the power factor is the ratio of the true power over the apparent power. So this is P over S total, 4026 over 4307 times 100%. This is 93.47%. with the given description, lagging. Lagging because the resulting impedance is actually J X of L. It is a motor load, right? So this is lagging. Oh, that is one definition of power factor. Actually, the other solution is that the cosine of the angle between the applied voltage and current, take the cosine, will still be the power factor. So the angle between the voltage and current is actually 20.85. 20.85. That's degrees. And one of the definition of power factor is the cosine of the angle between these two here. We will take the cosine. This is multiplied by 100%. What comes out is 93.45, same as this one. Or 93.47. Okay? Oh, that's it. So, if you are planning on taking the board exams, your solution should look similar to this, okay? And write legibly, vertically, and horizontally. Okay, this is Professor David J. De Los Reyes. So, for those of you who are planning to take up electrical engineering, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJ.DeLosReyes. If you want to share it, please click share. Okay, try to watch my long video format discussion on alternating current circuit. I am assuring you, you will learn something from it. Okay, good morning from Los Angeles, Professor David J. De Los Reyes.